Alright, welcome back. I'm Jason, and for this video we're going to work through some of the problems from your last week's quiz. I saw that there were some areas some of you struggled with, and what I want to do this week is review those, show you exactly how to work through the problem, and then I'm going to make that quiz available for a second shot for everybody. So one of the problems everybody struggled with had to do with the temperature entropy diagram and where are we on it and what happens when we add additional heat. So what I'm saying is, if we have a temperature specific entropy diagram which gives us a saturation curve that looks like that, where the critical point is all the way up here at the top, we can plot out a saturation process. We know that anything on this side here is liquid. And you saw this on that video where Jim and I were talking about it, and he talked through a phase change. And on this side is a vapor. And since we're talking about water, this is steam, and everything inside this curve under this saturation line is some type of steam-water mixture. So if you recall, anything over here, we have a point, and that point is based on some temperature and some pressure. And that temperature pressure gives that point some unit of energy. It gives it value. It gives it, hey, here's how much work it can do, and here's how much work it can't do. Now, assuming a constant pressure process, which is what we gave you, if we add heat to this system, the temperature rises until it reaches this saturation point, which is this point right here on the curve. That means it's at saturation. So specifically, the problem I gave you was 1 pound mass of liquid water. Liquid water at saturation conditions. So I literally am saying exactly this point. It is at its boiling point. If we look this up in our steam tables, whatever temperature I give you or pressure I give you, it is that saturation point, which means no more sensible heat can be added. This is all sensible heat on this side, and sensible heat on this side. However, anything in between here, this constant temperature process, is the latent heat of vaporization. And this is where that amount of water, that 1 pound mass of water, starts converting from 100% saturated liquid to 100% dry steam. So, any of these problems, any of these, hey, I give you some conditions, and I say at constant pressure the addition of 1 BTU of heat does what, right? If I gave you a subcooled liquid, if I said, hey, we've got a subcooled liquid that's down here, then I add 1 BTU of heat, well, that means the temperature goes up. And 1 pound mass, 1 BTU, that's 1 degree Fahrenheit. If I gave you a superheated steam, right? So I'm up here and I add 1 BTU. Well, the temperature goes up, right? Temperature goes up. But if I gave you a saturated steam-water mixture, I'm somewhere in here, it's a constant temperature. And all I do is more of the liquid gets converted to steam, which means the quality goes up because the moisture content goes down. There's less moisture in this as we move this way on our latent heat of vaporization line. There's less moisture, higher quality, it's drier steam. Now if I gave you dry saturated steam at a constant pressure, that means we're exactly at this point, and all of that liquid water is now converted to steam. And any additional heat past that raises the temperature. So it's all these types of questions, it's all about figuring out where am I telling you you are on this temperature entropy diagram? Where am I telling you you are in relation to this saturation curve? So that's why these definitions are important. You have to understand and figure out, am I subcooled? Am I right on the curve on the liquid side? Am I right on the curve on the steam side? Or am I superheated? Alright, so another question I saw some people struggling with is if I gave you some amount of saturated liquid at 280 degrees Fahrenheit. So you have the temperature. We're going to open up our steam tables to the saturated steam temperature, table 1, and we're going to find 280 degrees Fahrenheit. 280 degrees Fahrenheit gives us a saturation pressure of 49.2 psia and a specific volume of 0.01726 cubic feet per pound's mass. The thing to pick up from this question is the reason I'm using this V sub F, specific volume for a fluid, is because in the problem I gave you a saturated liquid. And that's what this V sub F is. That's what saturated liquid is, the specific volume of a saturated liquid, V sub F. Okay? 0.01726 cubic feet per pound mass. That's the specific volume for the fluid. Now, if I had asked you instead, if you have some amount of saturated steam at 280 degrees Fahrenheit, saturated steam has a different specific volume. Saturated steam is V sub G, the specific volume of a gas. But in the problem I asked you for a saturated liquid. And just like on the last problem, once again, this is why these terms, these definitions matter. Because when I give you liquid or mixture or steam or vapor, or I give you saturated or subcooled or superheated, those matter because I'm telling you exactly where on this temperature entropy diagram it is. I'm telling you whether you're above saturation, below saturation, subcooled, superheated. So the other part of this problem, so this first part of this problem was this direct lookup. You just look up the specific volume. Well, what seemed to confuse people was when I asked what the density was. Look at your units for specific volume. The units for density are the inverse. And it's pounds mass per cubic foot. So it's still a specific density is what we're asking for. Density is equal to 1 over specific volume. And in this case, 1 divided by the specific volume of the fluid. And just like the inverse of that, specific volume of the fluid is equal to 1 over density. So all we do is we divide 1 by the 0.01726. So you should end up 57.93 pounds mass per cubic foot. That's the density of a saturated liquid at 280 degrees Fahrenheit. For this next one, we're going to go to our Mollier diagram. So for this next one, I gave you steam at 920 psia. So first, let's find our 920 psia line, pressure on our Mollier diagram. Well, I'm going to be just slightly above the 900 pound line right here. So I'm not quite to that blue 1000 psia line, and the pressure lines are running this way. right? 500 pounds down here, 300 pounds, 200 pounds, 100 pounds. So this is the point I'm starting at. Well, how do I know that I'm starting exactly on that red saturation line? It's because in the problem I said with a quality of 100%. There's a couple different ways of saying that. I could say dry saturated steam at 920 pounds. I could say steam with 100% quality at 920 pounds. Either way, I'm saying the same thing, and I'm telling you that that's where that pressure crosses that red line. That steam is supplied to an ideal turbine. So you have to figure out, now that we figured out where am I telling you you're starting, what do I mean by an ideal turbine? Well, a turbine is a work process, but it's a constant entropy, isentropic work process, which means in an ideal turbine, we're going to go straight down with no change in entropy. All right, so let's draw a line straight down. But how far down do we draw it? Well, I tell you that the turbine exhausts to a pressure of 100 psi, which means I'm going to stop right here where it crosses the 100-pound line. So I'm going from here to here. Now, I could figure out a lot of things just from this information. Just based on what I've shown you, I know the starting enthalpy, I know the ending enthalpy, so I can tell you how much work that turbine did. Because I know this end point, I can figure out what the quality of this steam is. In fact, it lands right on the 18% moisture content line. And so what do I ask? What I ask is, what's the enthalpy of the exhaust steam? All right. Well, the enthalpy for this point is somewhere between 1,025 and 1,030 BTUs per pound mass. So I accepted anything from 1,025 to 1,030 BTUs per pound mass. Now the answer is closer to 1,027. But some of those charts you're working with are really small, so I accepted a range. I don't need you to nail it down exactly. Now if you did want to nail it down exactly, you can use this, you can see where it crosses the moisture content line, and the moisture content of 18% means 100 minus 18 is equal to 82% quality, right? So I could use my quality, and that quality times the H sub Fg added to the enthalpy of H sub F. And that would tell us that same final enthalpy. And take it into account that it's not 100% dry steam. It's somewhere down under this saturation curve. So I've got 1,027 BTUs per pound mass at 82% quality. And this was the easiest way to find it, was just plot it on your Mollier diagram. So again, understanding what the process is half of the question. And if I'm asking you a throttling process, I'm asking you specifically something different than a turbine process, right? A turbine process, like we worked through, was an isentropic process. It goes vertically on your Mollier diagram, constant entropy. A throttling process where steam goes through a steam valve, a governor valve, through some valves into a steam chest, is a throttling process, and that's a little different. So one of your questions, I gave you dry saturated steam at 1100 psia. Well, once again, it's really important that the dry saturated matters, right? Because that means we're on this red saturation line. So there's 1,000, there's 1,100. Make sure that next, yep, so 1,100. This is where we're starting. Dry saturated steam, 100 psia. I now know what that starting enthalpy is. It's just under 1,190 BTUs per pound mass. So 1,188 BTUs per pound mass. And I can confirm that with the steam tables. I could look up an exact value in the steam tables. And I would use H sub G for the enthalpy of that gas, because it's 100% dry saturated steam. Now, we're going to throttle through governor valves to 600 psi. Throttling process is a constant enthalpy process. So we're going to go across our Mollier diagram to 600 psi. To 600 psi, right here. So now I know what that pressure drop is. I know the change in entropy, because there's an entropy associated with this starting point of 1.38 BTUs per pound mass degree Rankine. There's an entropy associated with this final point of 1.44 BTUs per pound mass degree Rankine. So that's how much entropy was gained, how much more disorder, right? And you think about that. The steam is going through a throttling process. It's lowering pressure, it's expanding, it's becoming more disorganized, it's gaining entropy. But what I ask you is the final enthalpy. All right, well, the final enthalpy is the same as the starting enthalpy. So 1,188 BTUs per pound mass. I ask you the final quality. All right, so this up here, this red line is the 100% dry saturated steam. The next curve underneath the red one is 99%. The next curve is 98%. All right, so 98% quality. And I ask you the final entropy. So you draw your line down here, and the final entropy is 1.44 BTUs per pound mass Rankine. So once again, a throttling process is a constant enthalpy process and goes across. If I gave you a point right here and said you're going to throttle through some valves until it's 50 pounds, you're going to draw a line straight across till you get to your 50-pound curve. And to jump a little bit ahead, this week we're covering thermocycles. If we were actually having you plot some of those, I would give you starting conditions outside of the Mollier diagram, where you end up here. Then you have to figure out the throttling process across here. And then from here, what's the work process? How much work was done by a turbine to when we exhaust to a condenser, right? So you would go through and plot out an entire thermodynamic cycle. And you would calculate each leg of this. But we're not going to get into that. We're just going to focus on the concepts and do the processes one leg at a time. So that's a few of the problems that you saw in your quiz from last week. Once again, I'm going to make this quiz available. You're going to get a second shot at it. Make sure you review this. Make sure you work through these problems this way. Make sure you're paying attention to the definitions, right? The terms. Is it subcooled? Is it saturated? Is it saturated liquid? Or is it saturated steam? Right? This is saturated steam here. Saturated liquid doesn't even show up on your Mollier diagram, but on your temperature entropy diagram, you have the liquid side and the steam side. Your quiz for thermocycles for this week will be a lot of this again, asked a little bit differently. I'm going to change the values up. I'm going to change exactly which one I'm asking you. Maybe it's saturated steam instead of saturated liquid. Maybe it's some mixture. But you're going to have to solve these problems by both using the steam tables for some questions and the Mollier diagram for some questions. As always, if you have any questions, make sure you use the questions for the professor discussion post and message me. I hope everybody has a great week. Thanks. Bye.